Hello and welcome Physics C students to the first notebook video for Unit 3 on work, energy, and power. Talk about these two gentlemen here who are pictured. On the top we have James Prescott Joule. He lived from 1818 to 1889. And he was an English physicist, mathematician, and brewer. He studied the nature of heat, and this led to his kind of discovery of the law of conservation of energy, which in turn led to the development of the first law of thermodynamics. The SI unit for energy is named in his honor, the joule, abbreviated with a capital J, and a joule is a Newton times a meter. Of course, anytime you have a unit named after you, pretty big deal. The gentleman on the second picture is James Watt. He lived from 1736 to 1819, so he was Joule's predecessor. The unit of power is named in Watt's honor. A watt, a capital W, is a joule per second. I already see a connection between power and energy. It turns out that power is the time rate of change of energy. James Watt was also he wasn't English, he was a Scottish inventor and engineer and chemist who improved the steam engine. He didn't invent the steam, but he improved the efficiency of it, and that greatly aided the Industrial Revolution. So there we go. Two James that played major roles in kind of the history of energy. Let's take a look at the equations that are on the new AP Physics C equation sheet. First up, we have a kinetic energy equation. The kinetic energy, 1/2 mv squared, that's mass times velocity squared. It is interesting to note here that because velocity is dependent on your frame of reference, that kinetic energy is not an absolute quantity. It depends on the frame of reference that you take. If you are on a train, watching another train go by you at the same speed, it's essentially standing still. That would have no kinetic energy from your frame of reference, whereas if you are stationary on the ground watching the train go by, it has a lot of kinetic energy. The next formula, work, is the integral from A to B of force dot product with a little tiny vector dr. Dot product, I like to put a bigger dot in there. And this is a path integral, path dependent. So sometimes if you take a curvy path versus a straight path, you can get a different integral. Not all forces, though, depend on the path that you take. A force like friction definitely depends on the path. The longer of a path you take, the more friction you're going to have, because every little bit of the path has friction. But a path like gravity, a force like gravity is not path dependent. The difference between a force which is dependent on the path or not dependent on the path is the difference between what we call a conservative or a non-conservative force. A conservative force is a force whose potential energy or the work associated with it does not depend on the path that you take, and a non-conservative force depends on the path that you take. Much more on that later. The next formula down, delta K, here, change in kinetic energy is the sum of the work, and work is the force parallel times the displacement. We can see how this integral here, if we have a constant force, this integral would just become FD cosine theta, which you know from physics 1. This formula here, the change in kinetic energy is equal to the sum of the work done. That's called the work energy theorem, and it's important to note that this is only for a single object. This does not apply to systems. The work done on a single object, if you add up all the work done on it, is equal to the change in kinetic energy of that object. Change in potential energy is the negative integral of a force. This is a conservative force. That's what CF means. Conservative force, which is a force that's position dependent, dot product with the little path element dr again. And if you integrate conservative force over the path that you take, you get the change in potential. We'll go through several derivations for calculating potential energy functions for springs, gravitational fields where the value of G does not change, like when you're close to the surface of the Earth, and we'll also derive the universal gravitational potential energy formula, which is where you have very, very large changes in height, so the value of G is not constant. This would be like the difference in potential energy when you have an object on the surface of the Earth and then you put it up into orbit. Then we've got this same formula basically rearranged here. This is the formula in integral form, this is the formula in derivative form, and it's saying that you can get a function for force if you take the negative derivative of potential with respect to position. We'll see some examples of that later as well. That's force from potential energy. This formula should look familiar. The potential energy of a spring is 1/2 kx squared. You could also call this elastic potential energy, although we're using spring here because when we get to second semester electricity and magnetism, we'll also study electric potential energy, which will be U sub E. So to prevent confusion, we use S for spring and save E for electric later on. Then we have gravitational potential energy. This is over large distances where the value of little g is not constant. Notice that the potential energy due to gravity is negative. That's because we define the zero level to be out at infinity. Why is the zero level for gravitational potential at infinity in this context? Because when you're dealing with things on an astronomical scale, the moons, the planets, the stars, they all have different sizes. So the only convenient spot that works for all objects, no matter what their size, is to define zero potential energy to be when the objects are infinitely far apart and they have essentially no gravitational interaction. Then we have a familiar formula. Potential energy is basically mgh, or change in potential is mg times change in height. This formula is only true when the value of g is constant, so close to the surface of the Earth, or if you were out in space and you don't move position very much, the value of g would basically be constant there. Then we get to some power formulas. The formula for average power is work divided by time, or change in energy divided by change in time. Work is change in energy. Get into that later as well. Then we have a formula here for instantaneous power. Instantaneous power is the time rate of change of work. We could also say, because work is energy, that this is dE dt. And one last thing to note here, this is not on the formula sheet, but it is something that you want to know. The change in kinetic energy plus the change in potential energy, and this would include all forms of potential energy, elastic or spring, gravitational, and electric. So the change in kinetic plus the change in all types of potential is equal to the work from external or non-conservative forces, the work done on the object or the system from external or non-conservative forces. You've noticed a bunch of times we've mentioned conservative and non-conservative forces. We will talk about those more to come, but that's going to be something that you definitely want to understand the differences between. Okay, on the next page, we've got a flow chart here that we're going to fill out, starting with work in the top left corner. Work occurs whenever a force is applied to an object. That object has to be moving, and the force and the displacement of the object cannot be perpendicular to each other. So if you are holding up a box and you're walking sideways, you're pushing up on the box, but the displacement is sideways, that's perpendicular to each other. That does not involve any work. So there's really like 3 conditions under which you will have no work that is done. If you have a force which is equal to 0, you have no work done. Or if you have no displacement, you have no work done. So you can, if you just hold the package out and you're pushing up on the package but it's not moving, you can hold it there for as long as you want, but no work's done. You can push a wall as much as you want, but you're not doing any work on the wall if the wall doesn't move. The last way that you could have no work done is to have your force be perpendicular to your displacement, which is a 90-degree relationship, which we previously talked about. So there's some basics about work. The next quantity is energy. Energy is the ability to do work. And if energy is the ability to do work, that means the ability to exert a force. Right? Work is a force over distance. So if you're going to do work, you got to exert a force. And the last quantity that we're going to have up here is power. And power is a measure of work per unit time, or a measure of energy per unit time. Being powerful means that you have a large change in energy in a relatively short time. If you think about like 2 cars, one that you would think is more powerful than another, like a sports car, both cars, a sports car and your average, cheap sedan or something, your entry-level car, both of them can get up to 60 miles an hour. Getting up to 60 miles an hour would take the same amount of work if the cars had the same mass. The difference is that the sports car can get up to 60 miles an hour in a much shorter amount of time. Same work in less time. Or if both cars were given the same amount of time, both cars could go for 10 seconds. in the same amount of time, the more powerful car will do more work. More powerful car will get going faster in the same amount of time. Now, work is the same whether you are running upstairs or whether you are walking upstairs. And it's important to note that when we're walking or running here, we have to do this at a constant speed. So you run upstairs at a constant speed, you walk upstairs at a constant speed. The work that you do is going to be the same, but the power is not. When you run, you're getting up the stairs in less time. So you're doing the same amount of work in less time when you run up the stairs, more power. When you walk up the stairs, it takes more time to do the same work, and that is less powerful. We can note here that work is a transfer of energy. The work transfers energy from one object to another, or into or out of a system of objects. And energy has units of joules, and a joule is a Newton a meter. Power has units of watts, and a watt is a joule per second. At the bottom of the page, we have another little chart here. This chart is for the work energy theorem. And the work energy theorem basically says that if you take the sum of all the work done on an object, and it is not zero, and work is a scalar quantity. It could be positive, it could be negative. Positive work symbolizes a gain in energy. Negative work symbolizes a loss in energy. So if you add up all the work done and you get zero, you have no change in energy. If you add up all the work done and the sum is not zero, then the total amount of kinetic energy for the object will change. Now, this is only true for a single object. And single objects cannot have potential energy. Potential energy always involves at least two or more objects, because potential energy involves like some sort of positional relationship. So for one object only, you add up all the work done on it by either any type of force, conservative, non-conservative, doesn't matter. You add up all the work done. If it's not zero, then the object will change kinetic energy. If you have a positive amount of work, the object will increase its kinetic energy or speed, and we'd get kinetic energy final will be greater than kinetic energy initial. And if you have negative net work, the object speed will decrease and our final energy will be less than our initial energy. Another way of writing this is that the net work done, which is of course the sum of all the work is equal to the change in kinetic energy. And this is for a single object, not for a system. All right, that's going to finish up our first video. We'll see you shortly for part 2.